wonderful conjecture. It was one of my favorite problems to think about in grad school. It's a very notorious problem. Yeah, I think I just always loved thinking about it, and I was always satisfied thinking about it, even if I didn't solve it, just because it was so open-ended and so much fun to think about. So just to give an example of a union closed family, so here's a collection of sets, and there's a bunch of sets in this family, so you'll have to trust me that for every pair of sets, the union is in the family. So just as an example, the two red sets, 4 and 5, and then the set 2, 4, 6. If you take their union, you get the green set, which is 2, 4, 5, 6. So for every pair of sets, we get another set in the family. So that's the assumption of union closed. And the conjecture is that there's always an element that's in at least half the sets. So in this example, the element 4 appears in 16 out of 25 of the sets. So the element 4 satisfies the conjecture because it's in at least half the sets. Okay, so I don't know a lot about the history of this problem, but from what I've read, that it sort of went viral, at least as much as a problem could go viral back in 1979. It was being talked about at conferences. People were calling each other. There's this quote I found from a Dutch article on the problem, which was a bunch of people talking about the conjecture. I think there was a lot of excitement over it when it first appeared. And it sounds like maybe no one really knew who conjectured it. Like it just was a lot of hearsay, and at the time, no one really knew that Peter Frankl had conjectured it, which was unfortunate for Peter Frankl because he was a young mathematician at the time and not very well known at the time. And so, but it took some time for the community to realize that Peter Frankl actually indeed was the person who conjectured it. Anyway, so that was the conjecture, and it was really not much progress for quite some time, despite the fact that it's a very simply stated problem. So recently I uploaded proof of the following theorem that if we have a union closed family, then there's an element that's in at least 1% of the sets. And this proof uses information-theoretic techniques. So just in this talk, what I'll focus on is just how did I finally think of entropy with this problem, because I spent quite a bit of time on it in grad school and never thought about entropy, but there was a certain chain of thought that led me to the proof. But most of the work was really getting to conjecture something about entropy with this assumption. And it's interesting because none of that work is in the paper, but hopefully in the talk I can illuminate sort of what the journey I took with the problem, at least. Okay, so first, just a bit about myself. So I did my PhD in combinatorics and theoretical computer science at Rutgers. I was supervised by Mike Sachs, graduated in 2015, and I left academia. So my first job outside of grad school was I did applied machine learning at Bloomberg. And then I applied to the Google Brain residency program, and ever since then I've been doing research in deep learning. So I specialize in graph neural networks. I've done research in robustness to distribution shift, and I guess my current research focus is actually on optimization. But during this time, I really was out of math. I hadn't thought about combinatorics really since I graduated. And my last theoretical math publication was in 2015. And one thing I realized when I made this slide is I guess I like to think about notorious problems. But I think I like the open-endedness of some of these problems, and it's fun to dream. So anyway, so if I really haven't thought about math since 2015, why am I giving this talk? Well, in October last year, I was in New York for a friend's wedding, and I took a break to drive down to Rutgers to have lunch with Mike Sachs, my advisor, and we had a great chat. He told me about his textbook that he's working on. I told him about some machine learning research I've been doing, and we didn't really talk about math or anything. So after lunch, I'm walking around Rutgers, just kind of reminiscing my time at grad school, and for some reason, the union closed sets conjecture popped in my mind. It's a very sticky problem. I think just it's so appealing that I don't know. If there was one problem that was going to stick with me since grad school, it'd probably be this problem, just because it was such a joy to think about. And I started just thinking about the problem kind of casually on the walk, just for fun. Didn't really think to make any progress on it, but something kind of surprising happened on this walk, which is I kind of had a eureka moment for the problem where I won't spoil yet what this eureka moment was. It had nothing to do with information theory, this insight in the problem, but I thought about the problem in a different way that I had never thought about before, and I sort of immediately felt that this insight I had was interesting. And so for about 2 weeks after this eureka moment, I was basically thinking about this problem with any free time I had, and it was kind of an exciting time. It was, and let's see. So during those 2 weeks, I formulated 2 conjectures, and I won't say what these conjectures are yet. We'll get to them, but when I made this conjecture 2, I sort of knew that this had to be the key to the problem. And I write "knew" in quotes because I have felt many times on problems that this insight I had on the problem was the key, but all those previous times I have been wrong. So I've made many false conjectures, and I've known the feeling of like that sort of deflated feeling where you think you have some insight in the problem, and but then you find some counterexample that just completely kills your attack. But I thought maybe, but maybe this time, this was the time that I would be right. And what was it? Nope. This conjecture 2 was hilariously false. And this is just sort of giving the timeline on the problem, but I really almost gave up. Like I had this eureka moment. I made this conjecture that was very false, and then I almost gave up. It kind of was like a reality check for me. I was like, well, I hadn't thought about math for 6 years. Like, what am I doing thinking about the union closed sets conjecture? There's just like there's no way you would ever solve it. Like, I'm wasting my time, and I really almost gave up there. But there were 2 things that sort of gave me courage and kept me going. One is I did a lot of research online. In particular, I found the Polymath project, and I was fairly convinced that no one had this original eureka moment. That like this eureka moment I had was actually new, and that this conjecture 1, this other conjecture, was new. So that kept me going. And anyway, long story short is worked on it for another week. Something finally led me to entropy. I'll explain what that is later in the talk. And so about 5 weeks after my initial insight on a walk, I had a proof. So in this talk, I just want to sort of go into what happened during these 3 weeks that sort of led me to finally think of entropy. So I guess I'll talk a couple of things. So I'll discuss, why is this problem notorious? What was this original eureka moment? What was this false conjecture 2 that when I realized it was false, I almost gave up. But at the same time, this like false conjecture is also really what guided me towards to think of entropy, was refuting this conjecture and studying the counterexample I had. And then at the very end of the talk, we'll give a brief discussion of the proof, but we won't focus too much on the proof. So anyway, so to get a sense of this problem and why it's so notorious, so I'll start with one of the most common partial results that is known for this problem. So it's relatively easy to show that if you have a union closed set F that contains a singleton, meaning a set of size 1, that such a family must satisfy the conjecture. So the way to show that is, so if you have a singleton, and you can consider basically all of the sets in your family which do not contain your singleton. So in this case, I've highlighted in green all of the sets which do not contain 4. And so if you, the observation is if you take all these green sets which don't contain 4, and you take 4 union all the green sets, you get all the red sets. And the observation is that this, because 4 is a singleton, this union operation is an injection, which means that for every green set which does not contain 4, I have a unique red set which does contain 4. And then every other set that's not in the image of this map must also contain 4. And so basically we've shown that because the red sets are at least as big as the green, 4 must be in at least 50% of the sets. Okay, so that's one of the easy special cases you can show for this problem. A similar argument works for if your family contains a set size 2, which would lead you to think that maybe this strengthening works. So so let S be a non-empty minimal element of F, then S contains an abundant element, which means that S contains an element of an element that's contained in at least 50% of the sets in F. And so yeah, the statement turns out to be false. I won't go into detail of the construction, but to give some intuition, what really happens is if your minimal element is big, then this subfamily, the family you get when you take S union everything in your family, this subfamily may be really small. And so there's no way to take this minimal set and force any abundant element in your family, just because this set of all unions you get just doesn't cover very much of F. Okay, so that's one of the false strengthenings to a pretty natural attack on the problem. Here's another false strengthening. So you can ask, well, okay, what if I consider an average element? So, let's, for each element in our family, let's take all of the elements, let's consider the number of sets which contain that element. And, maybe on average, an element is contained in at least half the sets. And so this strengthening also turns out to be false. So this construction I've given here shows why. So this is a family with 4 sets, and it contains one set that basically has a ton of elements, and most of the elements are just not interesting. So the elements 3, 4, 5, 6, 7, 8, 9, 10, 11, they only appear in one set, and I've just sort of artificially thrown them in to basically kill this averaging hypothesis, because most elements are in that giant set, which is only in 1/4 of the sets. Okay, so this, I guess, this is sort of the story of this problem. There's many natural strengthenings of this conjecture, and it's just that they all turn out to sort of be false. And I think Gilmer summed it up pretty well with that he remembers Jeff Kahn says he will bet that he will find a counterexample to every meaningful strengthening of Frankl's conjecture. And this is sort of like what it was like to work on this problem. You would try to find some averaging argument, and no averaging arguments seemed to work. You would think about it, you come with a counterexample, and it just really felt like we couldn't get our hands on the problem. And so just why this problem was so notorious. It's one, it's so appealing. It's so open-ended. And when you're thinking about trying to solve it, there's just so many things you can try. There's induction arguments, there's averaging arguments, there's set system operations, and you're really just trying to understand, well, what is the structure of union closed families? And if you think about it, at least for me, having worked on it for so long in grad school, I mean, you come on to the conclusion, which is just there's no structured union closed family. Anything you try, anytime you try to grab your hands on a union closed family, it just sort of like shifts away from you. It's like trying to like I don't know, like pick up water with your hands or something. It just slips out of it just slips away from you. So then what was the eureka moment for me? Like how on an hour-long walk did I come up with some inspiration that led me to eventually make some progress on this problem? Well, it really was to consider the contrapositive. And that's kind of crazy to say, but this is a bold statement, but I think I might be one of the first mathematicians to seriously consider the contrapositive for the union closed sets conjecture. I think just something about how this conjecture was stated, I think we all forgot that there was a contrapositive. I think it's such an elegant problem that why would it be stated any other way? And just to get some evidence for this, so you can look at the Polymath project on Tim Gower's blog. So for people who don't know, so the Polymath is when a large group of mathematicians get together and we're all going to work together to try to solve some notorious problem. And a lot of interesting ideas on this Polymath project. Actually, the first comment I thought was interesting, which is, let's try to prove that there's an element that's at least 1% of the set. So that was a good idea. But if you look for a contrapositive, there's 148 responses to the first round, 0 mentions of contrapositive. You look at the second round, 0 mentions. You look at the third round, there's still no one has ever mentioned the fact that every conjecture has a contrapositive. Fourth round, nothing. Fifth round, nothing. And eventually the project ran out of steam. So one thing I'll say is that I think, at least reading online, it sounds like many consider this Polymath project a failed project, but for me, it was actually very valuable just being able to read the Polymath project, because the main thing that I struggled with when I was working on this problem, where I had what I thought was some new insight into the problem, but I needed some confirmation that this actually was a new attack. And the best confirmation I had was reading the Polymath project and confirming that no one had thought about the contrapositive, because that's kind of a crazy I think when you're thinking about these notorious problems, like your main thought is, surely every thought I have has been done before. Everyone's thought about this before, so why try? And that is especially true if your insight into the problem is to think about the contrapositive, because surely everyone must have thought about that, but apparently maybe not. So, okay, so why was the contrapositive my eureka moment? So, so here was my first thought. So, okay, so so we're going to show that we're going to assume that we have a family F that has I guess there's no element that's contained in many sets. And actually, in the extreme case, you can suppose that there's no element that's in more than 1 over size of F of the fraction of the sets, which is another way of saying that there's no element that's in more than one set. And in that case, your family is basically a bunch of just mutually pairwise disjoint sets. And so every union you get is going to give you a new set. And so because there's basically size of F choose 2 unions you get basically the number of unions you get when you take all pairwise unions it grows quadratically in the size of the family. So, okay, so that was nice. And then you can think about basically just another natural family of, I guess, sets that has very small size is you take all the sets that have size p times n. And when p is small, I guess you take all pairwise unions, you basically get all the sets that are drawn in the green line in this picture, which is all sets of size roughly 2p minus p squared times n. And so as p gets really small, you basically the number of unions you get is roughly quadratic in the size of the family. One interesting note about this construction is when P is 3 minus square root of 5 over 2, which is roughly 0.38, then that's the point where the size of the red line is equal to the size of the green line, meaning that the number of unions you get is roughly equal to the number of, I guess, the size of your original family. And so, so that's sort of the natural, I guess, what do I say, like boundary point where that's where you transition from you get more unions than you started with to you get the same amount of unions, and then if P gets bigger, you get fewer unions than you started with. And it's worth mentioning while we're on this slide that, so I guess we now know that actually this threshold is the best possible for approximate union closed families. So approximate union closed means that instead of every pair of unions is in your family, what if 1 minus epsilon pairs are in your family? And so one of the follow-up works gives a construction which sort of looks like this picture. You take F to be all of the sets that are just above the red line. And if you take all their, you take that, and then you also take everything above the green line. Yeah, I guess maybe to say high level how this construction works, because you're taking F to be all the sets just above the red line, that is a large portion of sets, because as you move up in the Boolean cube, the number of sets in each level grows significantly. And so I guess the most elements in your family are down near the red line, and so that gives you the element abundance to be like P is like 3 minus root 5 over 2. Okay. But anyway, so I guess going back to this hour-long walk that I took, this was really the inspiration that I had. And so this led me to this conjecture. So there exists a P bigger than 0 and a constant C with the following property that if F is a family of sets where each element is contained in at most P fraction sets, then if we take all pairwise unions, we should get some like size F, we should get some, polynomial size bigger number of sets than our original family. And I really liked this conjecture because, if you think about all the like failed attempts, for example, suppose you were trying to prove the normal direction, and your proof starts with, let A be a minimal set in F, and consider, all sets A union B for B and F. This proof is a natural proof to start with, but this proof has barely used the union closed assumption. Like there's roughly size F, there's size F choose 2 unions. And this proof is taking one set in our family and considering all unions involving that one set. But really, to really get your hands on the problem, you need to consider all pairs of unions. And so this proof here, just trying to understand why all previous approaches failed, it's just because if your proof starts like this, you've barely gotten your hands on the family. Whereas this conjecture, just very cleanly uses the union closed assumption. It was, I can just count all pairs of sets in the family, and the reason why I was excited is I sort of felt like that was that this finally gets around what was so notorious about the problem, and really, I guess, seeing the Polymath project and confirming that no one else seems to have conjectured this before, that finally gave me the courage, okay, maybe this actually is new, and that's what led me to pursue it. But it was kind of a wild journey. It was many ups and downs, and I assumed the whole time that this wasn't going to work, but eventually it did. So okay, so that was my conjecture one. But So I mean, that was fun and it was exciting to find this conjecture, but now I had to actually try to prove it. And that was difficult, at least challenging for me, having not been and thought about math in a very long time. First thing I struggled with is I had no idea how to use this assumption that each element is contained at most, a small fraction of the sets in the family. I worked on it for a while, and eventually I formulated this conjecture. This is the conjecture 2. And so this conjecture reads, there exists a constant C with the following property. So any family F such that it's this, I guess I'm looking at this, the size of the average, pairwise intersection. So I'm taking all pairs in the family and looking at, how many elements do they share relative to, the size of one of the sets that I'm considering. And I'm supposing that, I guess for most pairs, at least, on average, pairs don't intersect in many elements. And I thought that maybe that was enough. This is a weaker assumption than, there's each element's contained in most a p fraction of the sets. But I don't know. At the time, I was actually quite optimistic about this conjecture. But this conjecture turns out to be very, very false. So there's a construction where basically the size of F union F is basically logarithmic in the size of F. Unfortunately, I don't have time to, at least I don't have a slide that explains the construction, but actually there is, this quantity 1 has appeared before in the polymath project. Actually, they considered this quantity when they were trying to prove the forward direction. There's a paper on arXiv that constructs a family F that kind of refutes this quantity is very small for the family F. And so my construction is kind of similar to that. So if you're curious, you can read that paper. Really, like, I guess what led me to entropy was really when I constructed a counterexample to this conjecture. And what I noticed in the counterexample is that, all of the interesting elements in the counterexample had high entropy. And the reason why I didn't get many, like the reason why the size, like the number of unions I got was very small, is because, for every element that had high entropy, that element was contained in basically all of the sets in my family. And so that finally led me to understand how to use this assumption that there's an element that's contained in most a p fraction of the sets. And so that led me to formulate this conjecture, which eventually became a theorem. So this theorem is, so there exists a p bigger than 0 with the following property. Let A and B denote independent samples from a distribution over subsets of n, and assume that for all elements in our family that I guess the probability that this element is in our set is at most p. You should also assume that the family has some entropy, and then the theorem says that the entropy of the union needs to grow relative to the entropy of the family itself. I realize I've been talking for a while. I just wanted to pause to see if there's any questions, and also just confirm that people can hear me.
Yes, we can hear you. Yeah.
Okay, good. All right. But yeah, don't hesitate to interrupt me if people have questions. Okay. So let me drink some water. Okay, so to give an example, suppose that suppose that our distribution A is just, each element is sampled IID Bernoulli with probability P. So in this case, the entropy of A is, each bit is independent. And so the entropy of independent bits, you just sum the entropies of the bits. And so we get n times h of a single bit, which is h of p. And then for the union, the probability that I is in the union is the probability that I is in either A or B. And that's where we get this quantity 2p minus p squared, which you'll notice is also the quantity that appears in the previous slide with the approximate union closed construction. But anyway, so h of A is equal to, I guess we have these two relations, and so yeah, again, like the point where they're equal is roughly when p is something like 0.3819. Okay, so that's I guess that's an example for the theorem. And okay, so why does this theorem imply the union closed, or apply a constant lower bound for the union closed conjecture? So that follows from the following argument. So if A and B are sampled uniformly from a union closed F, then the entropy of A union B needs to be smaller than the entropy of A, or at least smaller than or equal. And the reason is A union B, it's a distribution over F. This is by the union closed assumption. And the entropy of a distribution over F is maximized when it's the uniform distribution. And so, I mean, we get as corollary that if we have a union closed family, that there must be an element that's contained in at least 1% of the sets F, because otherwise taking a random element or taking two random sets in computer union would violate this theorem 1. Okay, good, I guess there's no questions, so I'll move on to the next slide. Okay, so now let's say a little bit about the proof. So we're going to reveal the bits of A and A union B one at a time, and we're going to show that, I guess for all I, that if I look at the entropy of the first I bits, that the entropy of the first I bits in the union is bigger than or equal to some constant lambda times the entropy of the the first I bits of A. And this to analyze this quantity, you can use chain rule, which is that the entropy of A is really the sum over all I of, I guess, entropy of AI given its history. And so it's enough to show just at each step that the entropy needs to grow. And so it's enough to show this quantity for all i's. So we're gonna look at the entropy of the union of a single bit given the history of the union. Make sure that's bigger than or equal to some constant times the entropy of, I guess the entropy of AI given its history. And there's nothing special about this 1.26. That's just the number that came out when I did the calculation the first time. And so, yeah, it's enough to show this quantity, but this was still a bit ugly to work with, mainly because the conditioning on the history of the union is still a mess. But luckily, I guess there's a lot of useful and very cool facts about entropy. So I guess luckily this inequality basically saves us. So the observation is that the entropy of the union given its history is bigger than or equal to the entropy of a single bit on the union given the individual histories. And the reason why this inequality holds is because the history of the union is just a function of the individual histories. And so, I guess the intuition is, when you're computing entropies, if I tell you something, if I give you some information about the quantity that you're computing, or at least if you condition on more information, then the entropy has to shrink. And so conditioning on the individual histories makes it so that the entropy shrinks. And so I guess we've reduced it to the following statement. So we just need to show that at each step, when we're revealing the bits, that this quantity holds. So this is the entropy of the union of a single bit given its history. This needs to be bigger than some constant times the entropy of a single bit given its history. Okay, and so I got to this statement, and I wasn't sure what to do with it. I guess the only thing I could do was really just write down the definition of entropy, and that led me to this statement. So this is a double expectation. So if you just write down what that entropy of A union B sub I given its history, it's really this double expectation over entropy of basically two two sequences of real numbers. So so when I got to here, I initially thought that this will just follow from Jensen's inequality, and got quite excited, but then realized that Jensen's inequality does not work. Unfortunately, the quantities here they're not convex in both P sub C and P sub C prime. So Jensen's inequality didn't work. I messed around with it for a little while, but I think at this point I was getting quite frustrated, and I wasn't having fun anymore, because again, I was doing all this in my free time, and so the main reason I wanted to do it is because I enjoyed thinking about this problem. And so anyway, I sort of threw my hands up in the air and just gave a very heavily unoptimized version using Markov's inequality. So I uploaded that 1% bound to archive. And I wasn't really sure what was going to happen. I was fairly sure that, well, I couldn't really tell how hard that inequality was. I was waffling between maybe it's actually really hard, or maybe this is like a first year analysis homework problem. I couldn't tell. But I was expecting maybe in a week I'll see someone uploads a paper that proves 10% or something, and that we would slowly walk towards what I thought the correct number was, which was 38.19%. That is not what happened. I uploaded the paper. I twiddled my thumbs. I thought I checked archive every day. I was quite excited to see what would happen. And 4 days, or yes, five, just a couple of days later, basically there were 3 papers all on the same day, which proved, which improved my 1% bound to 38.197%. And I would love to hear what was happening, I imagine that some of these grad students and professors must have pulled some all-nighters, because it was just really fast after my paper. And I mean, because it took me a couple of days just to work with that double expectation and get the 1%. And I don't know, I would love to just hear the other side of the story, what these people were thinking. And was it some bad panic to try to improve the bound? I don't really know what happened, but it was fun to watch. And so a couple of days later we saw these three papers that all got the 38.19%. The next day there was another paper which also got it. So this is 4 independent groups working. Then there was a lull for a couple weeks, and I guess on December 1st, there was a paper uploaded that proved the uniclosed sets conjecture for 0.38234. And this quite surprised me, actually, because when I uploaded, I was thinking that, sorry, maybe before I get into that. So there was this paper, and I guess where we currently are is Canby's result, which adds a couple more decimal points to U's result. And this is where we're currently stuck. And this is what was surprising to me, is that the natural barriers seem to be this 3 minus √5/2 and 50%. I did not expect that we would get stuck just above 38.2. I was actually a little nervous that within a week someone would prove 50%, and I actually missed some easy thing, but that didn't happen. So anyway, this is where we currently are, and I still check archive relatively frequently to see if anyone makes more progress. It's been fun to watch. I'm not actively thinking about it myself. I've returned to machine learning for the most part, though. Although I'll admit I have started to think a little bit more about some other conjectures, but we'll see what happens. Anyway, yeah. So that's the timeline. Yeah, question.
There's a question on the chat. So
yeah, great.
So Umang was asking if is there a specific reason where some of the authors are bold?
I'm not sure I caught that. What's the question?
Some of the authors like Savan, you, and Camby are in bold. So is there a specific reason for that?
Oh, yeah, good. So, sorry, yeah, I bolded 3 names here. I bolded Will Sawin, you, and Camby. And the reason why they're bolded is, I guess 4 days, I guess Sawin's paper sketched a proof of how to push just past this natural limit of 3 minus √5/2. And so this proof sketch was basically you and Camby sort of built off that proof sketch and sort of did the calculations to see how far that would push, and it ends up pushing just past 3 minus √5/2. And the main idea there is to so I guess the proof I used considers 2 independent samples, A union B, from the family F. Will Sawin's idea that was optimized by you and Camby was to consider 2 samples, A and B, and then a third sample that's sort of correlated with A in a special way. That's a very high level, sort of the basic idea, but you'll have to invite Will Sawin to explain more about that idea. Anyway, I hope that answers the question.
I had another question. Can you go to the previous slide, please? Yeah. So how did you prove this inequality, the expectation over CC prime inequality? Is this...
Yeah, okay, good. I didn't prepare a slide to really dig into that, but the main observation is that when P sub C and P sub C prime, when they're both small, like I guess the entropy grows. So it's if I take, like, suppose for example that all the P sub C were equal to 1%, then the left expectation, you're basically computing H of 2%, roughly 2%, and you're comparing that to expectation of H of 1%. And when P is small, the entropy grows, and so the inequality is satisfied in that case. And I guess where we use Markov's inequality is just to ensure that there's enough, I guess enough elements P sub C that are sufficiently small that the union grows there. And there's anyway, it's easier to explain if I had prepared a slide for it, but just the main observation, you just want to force a lot of density near 0, because near 0, that's where the left-hand side grows, and that's really the main idea.
Sorry, another question. So it feels like this is like an average case statement. Is that correct, or is that this statement about expectations feels like an average statement and not a worst case statement? Do you get that there are many elements which are contained in 0.1%, or do you really get this one element?
sorry, so you're right. Make sure I understand the question. So
so do you really do you really know that is one element, or do you get? I mean,
good. So this quantity here, expectation over C of P sub C less than or equal to 1, or sorry, less than or equal to 1%. That's basically the marginal of A. That's basically expectation of A sub I. And in other words, that's basically saying how likely is it that if I sample a random A in my family, does A contain I? And so that's exactly the assumption that, probability that A contains I is 1%. It's written in a weird way because of how P sub C is defined, but really this is just the like all elements are in at most 1% of the sets assumption encoded. And like the reason why there are these P sub C is that, this is P sub C represents what is the probability that the single bit A union B sub I is equal to 1, given the history. And what happens is, given the history, that there might be some histories for which that probability is really big. Right. So maybe when I'm revealing the bits A and B, maybe there's like a certain history, maybe all ones, where if I happen to sample that history, like the next bit A is very likely to be 1. But that history is rare, and so the marginal is still 1%. But there are these rare histories which condition on the history, the conditional probability jumps really high to close to 1. And so, so that basically using Markov's inequality, that sort of just ensures that there's not many histories where, like, there are these bad histories where condition on the history, the entropy, or I guess the bitwise probability is high. And so all we're just saying is not many histories for which that happens.
okay, thanks.
Yep.
Justin, sorry, one more question. So if I kind of understood this correctly, I mean, it seemed to me that you're somehow only using the fact that the pairwise unions are present, or maybe the 3-wise unions are present. Like, you're not using the full power of that it's union closed. Is that correct to say? I mean,
that's correct to say. I mean, this is really just measuring the right. Yeah. How much if I take all pairs of unions, how much does that entropy grow? And yeah, so it is a natural question. And well, right. So we could look at the entropy of, all 3-wise, or I guess all 3 tuples. And I think what happens is, when you go to that next step, you don't really get anything that actually the pairwise unions is basically the limit. I mean, or meaning that you just don't get any boost from going to all three tuples.
Okay.
But yeah, it's a natural question. It just doesn't help us, unfortunately.
Okay, thanks.
So I had one more question. So right now, do we know that this inequality holds when under the assumption that this expected TC is just 0.38 or something?
Sorry, can you say that again?
Do we now know that if you just assume that expectation of TC is, let's say, 0.38, then the above inequality holds?
Sorry, so you're saying if we assume the expectation of P sub C is at most 0.38.
Right.
So under that assumption, the above, I guess you don't get the 1.26 anymore. You get like a weaker constant, and really the opposite
is that constant is just above 1, right?
Yeah, I mean it's like if you deviate from 0.38 by some very small epsilon, then that constant is like 1 plus some epsilon prime.
Okay. Okay.
Yeah, and good. I mean, this construction that I showed before, where you take F is all all sets with size exactly 0.38. That's when the entropy of the union is equal to the entropy of A, and so that's where it no longer grows.
Okay.
And that's why that quantity was the natural barrier, at least so I thought. But it turns out that there was this small argument, or the small improvement from Wilson that pushed us just beyond that, using this correlated sample idea. So I don't know, I will admit I don't fully understand why the barrier is just above 0.38. I didn't expect it, and I haven't, because I haven't really been actively working on this problem. I haven't really fully digested all the follow-up work. So I apologize if people are disappointed, but I'm not the person to ask about all the follow-up work. So okay, but yeah, are there any other questions? This is basically my last slide. So.
Okay. Okay, let's thank Justin for the talk. Any further questions online or over here? Okay. Yes, if there are no further questions, let's thank Justin again for a really nice talk.
All right, thank you.
Okay, so what do we need to do? Just say stop the next.